Hello, dynamics students. This is another lecture in discussions on particle kinematics, and this lecture will include two examples of cylindrical coordinates being used to describe or to create equations of motion. So in some previous lectures, I derived the expressions for velocity and acceleration for cylindrical coordinates, our time derivatives, and now we're going to put those expressions to use for a system that is very well suited for a polar or cylindrical system. So in this one we have a bar with a slot in it, and so the bar extends into the screen basically. So we're looking at a cross section of it, and it's pivoting around its center point, and it's being kind of shown as a sort of a hinge, but you could think of it as a shaft. So this could be like a bearing, and then there's a radial slot. And there's a rod or maybe even a sphere that's sitting in the slot, and it can slide. And as the rod turns, so as theta increases with time, this rod P is going to move outward in the slot. So it's radial movement in the slot. Maybe somebody took some time-lapse photography and found that we could describe its radial position versus the origin here as 3t squared divided by 2 meters. And we have a constant turning speed and angular velocity of the disk with a scripty d or rod cross section is 4t squared divided by 3. So that's what the angle here is going to be with respect to time. So it's definitely not a constant turning speed. It sounds like it's accelerating in the theta direction. So we need expressions for the pin's acceleration and velocity at a particular time. So velocity would be related to maybe two expressions for momentum. If we needed to use conservation of momentum, if it was the rod was going to impact something and we needed to examine a collision. An expression for acceleration opens the door for in our kinetics studies to start relating what the motion of that rod to forces. So the minute we have acceleration, we can go back to force through Newton's second law. And then once we have forces, we can start looking at stresses and material properties and designing parts. So kinematics, motion will eventually lead to the things that create the motion or keep the motion from happening. So trying to give a little bit of practical context. How we would have gotten that theta expression could be determined by a motor controller speed, and again, this R expression could have been measured with some image analysis photography. Okay, so let's go ahead and use our hard-won derived expressions for cylindrical coordinates, and let's just start putting in functions. So position at any time. We don't have anything in the z-axis, so we have no k-hat component. So our position is just r hat. So r is 3t squared over 2 in the r hat direction. We know that our velocity at any time is just the time derivative of this expression. So basically we end up with r hat dot, use a derivative of a product and then put in our expression for the time derivative of our r hat, and this should be r. There's a little typo here. Basically the time derivative of this whole expression, which is velocity. Okay, so we can put in our time derivative for r, which is just going to be our 6t divided by 2, or 3t. We will need an expression for our theta dot or our d theta dt. Well, we have an expression for theta, so we can just take the first time derivative of that and get 8t divided by 3 and plug them in. So here's r dot in the r hat direction, there's r, and there's theta dot, and that product pointing in the theta direction. So now we have a complete expression for the velocity in terms of r hat and theta hat. Doesn't make a lot of intuitive sense, but we know basically the velocity of this pin or little ball, how quickly it's moving outwards and how quickly it's moving around. Okay, so now next up is acceleration, and we're going to start with our general expression for acceleration in terms of r hat and theta hat. And again, this is the one that we derived in some earlier lectures. And we can take the second time derivative of r. Remember, our first time derivative was 3t. Now we just take another time derivative and we get 3. And we do the same for theta. So acceleration for both of these expressions is constant. So, but those are not the only components of acceleration in each of the orthogonal directions, the r and theta. So just one part of them is constant. So we'll go ahead and plug these in. So r double dot is 3. We've still got the r dot theta dot, so we have, again, 2. We've got the 3t, 8t over 3, and just continuing to plug and chug. Constant expression here multiplied by r, which is going to be a t squared expression, and then our r again, and then our theta dot all squared. So just plugging in again the kind of the scalar term time derivatives, where they go, and associating them with their proper unit vectors. Now do a little simplification and then again combine terms, and you can see here's the scalar component of acceleration in the r hat direction. We could kind of call that like r hat, maybe ar. We could call this a theta. And so these are combinations of second time derivative changes in their respective directions, and then the other components coming from those orthogonal unit vectors that we derived last time. So that's why we still have time dependence in these, and why they're a little bit more complicated terms. But everything in parentheses here is pointing in the r hat direction, and everything in parentheses here is pointing in the theta hat direction. So now we take a time of interest of 1 second, and we substitute it in for t in both this acceleration expression and up here in the velocity expression. And now we can get some constants. So at 1 second, our velocity is 3 in the r hat, plus 4 in the theta hat meters per second. And acceleration, we have negative 23 over 3 in the r hat direction. So notice that's pointing in a different direction than the velocity, definitely. And 20 in the theta hat. And if we were to express these as vectors, we putting in 1 second into our expression for theta, we would note that theta went from 0 down here, kind of is parallel to our Cartesian I hat, and it is now gone all the way up here to 76.4 degrees. Our velocity vector is pointed off in this direction, and our acceleration is pointing kind of down and more back towards the center at that particular instant in time. So if I wanted a total magnitude of acceleration, I could do Pythagorean for these and get a total magnitude, and that would be my force resultant. And then I could also look at what effectively would be the force resultant in each of these directions and say, gosh, what did it take to get these? But not important for kinematics, but just giving you an idea of why would I need this expression? What would I do with it? This acceleration expression would be my launch pad into forces if I knew the mass of this little rod or ball or whatever it was. Okay, so that's first example of using our cylindrical, or basically our polar coordinate expressions. So now we're gonna pick up that k-hat direction with some true cylindrical coordinates. So we've got a point Q, and it's moving in a spiral stretched out into a helix. So it's moving at a constant speed of 20 meters per second. So speed, okay, we're going to have to interpret what does speed mean in this context. And we're given a cylinder radius and a pitch. And so a pitch means how far up do you go with every revolution around. So it's basically a dz d theta, with theta being 2 pi all the way around. So we can basically start expressing something about position in terms of what we're given. So we know that r is always the same. It's traveling around the surface of the cylinder. So r is constant, and it's a half a meter. And so r dot is also, it's 0. R is not changing, and r double dot is also going to be 0. So it's not sinking into the cylinder, and it's not flying off the cylinder. It's tracing right around the surface of the cylinder. So we can express our z position in terms of theta. So remember, theta can just keep going round and round and round. So when theta is 0, we're at a 0 here. With one loop around, theta is 2 pi, and we've gone up 0.2 meters. If we go around 4 pi, so 2 revolutions, we should be at 2 times 0.2 meters, and so on. So we can express z in terms of theta using our pitch definition. So just these two give us our position vector. So in terms of cylindrical, so we have 0.5 meters in the r hat direction, and then we have our z expression in terms of theta in the k hat. Let's take our first time derivative. So we end up with r dot in the r hat direction plus r theta dot in the theta hat direction. So we're not seeing the r hat direction because r dot was 0. So we have 0.5 meters times theta dot times in the theta hat direction. And then we're going to take the time derivative of this expression. Well, the 0.2 meters divided by 2 pi is a constant. Theta, time derivative of t is theta dot. K is not changing direction with time, so it stays the same. Okay. So speed. Now I got to think, what is the definition of speed? Well, if we go back to our physics, we can remember that speed is the magnitude of velocity. Oh, but velocity's got 2 components. Which one do I use? Oh, magnitude of a vector, we can just Pythagorean the magnitude of its 2 components. Meaning we can square them, add them, and take the square root. Apply the Pythagorean theorem. So the speed squared is just going to be the sum of the squares of the magnitudes of our 2 component vector components, which is the one in the theta hat direction and the one in the k hat direction, which are the only 2 components we have of velocity. So our speed of 20 meters per second, if I square that speed, that's going to be the sum of the squares of the 0.2 meters over 2 pi times theta dot, and then theta dot times 0.5 meters. So square both of them, add them up, hey, now I have a theta dot squared in both terms that I can factor out. And so now I have a way to express the d theta dt, or angular velocity, which turns out to be about 40 per second, 40 hertz, which I can now put back into my expression here and here and get a total velocity expression, which I'm finding is, in this case, is not time dependent. It's constant. So, but is acceleration going to be constant? So let's go ahead and keep taking some derivatives here. So if I wanted to find acceleration from velocity, I would take the derivative of a product and add that to a derivative of another product. So let's just go ahead and start that. So to find, let's go back to our velocity expression in terms of theta dot. So we'll end up with 0.5 meters times theta double dot times directed in the theta hat direction. And then we're going to have to subtract effectively the time derivative of theta hat. So that's our r theta dot squared er hat. So that's the next term in our acceleration expression. Well, we already know that theta dot is 40 second to the negative 1, so we can put that in. We know that the radius is 0.5. We know the radius is 0.5 here. And then we've got, again, a theta double dot. If theta dot is a constant, theta double dot is 0. So I really could have just taken that first term as 0 from up here because these two are constants, but I wanted to show how we'd taken the derivatives back from our velocity expression before we use that constant speed to give ourselves constant values for our d theta dt. But in any case, this term and this term go to 0 because of this. And so the acceleration is all in the r direction. That's all we have. We just have acceleration in the radial direction, keeping it going basically in a circle. So while it has velocity in the theta and k directions, it only has acceleration in the radial direction. So moving around on that helix, that helical path. Okay, we're gonna go for our last and related topic. I know this is getting to be a little bit long, but I'm gonna go ahead and try to pick up our tangent normal coordinate system, which is super useful for something traveling along on a path, and that's because it's very, very similar to our cylindrical. And in fact, if we define a path as being a helix or being in a circle and constrain something to move in that such that we weren't changing radius and we were forcing something to move in a certain way in the z direction, we would find that our cylindrical, full expression for cylindrical coordinates and this normal tangent were the same. What's cool about a normal tangent is you don't have to be on any particular path. You can define that path later on. So if you know something about the path, whether or not you know as much about time, this system is a little bit easier. So this is kind of our last coordinate system, and it's called the NT, or normal tangent system. So again, it's for a curvy path, but not any particular curve. We'll find out it's for any kind of curve. So we're going to define velocity and acceleration in terms of directions tangent and normal to a path of travel. So we're going to start at a reference 0 point, our starting point out here in space with a little hatched marks kind of indicating this is maybe some starting surface that we're is our starting gate. And we're going to move along this path. And the distance we've traveled as a function of time is s as a function of t. It's the path of point P. So it's in some kind of length units. And if we define a reference coordinate system point, which is not the same as our starting point on the path, but we've got a reference point in some kind of reference frame F out here, we can draw a radius vector to a point that's on the path, and we can call that ROP. Sounds pretty familiar here. So we can define ROP in terms of t or in terms of the length of the path we've traveled, which is itself a function of t. I'm sensing the chain rule coming up here. I got the function of two things. So I'll take the time derivative and say the velocity of my point P with respect to my reference origin O is r dot OP, which is the time derivative. So now I'm going to express that time derivative, which gives me velocity with respect to the origin of my reference frame, in terms of the path, not just time. So dr dt is equal to dr ds times ds dt by the chain rule. Okay? So I've got something now that's a little bit esoteric to define, dr ds, and then ds dt is really the speed tangent to that path. So this is going to be kind of akin to like my dr dt or my d theta dt, really akin to my d theta dt. And so it's basically how fast something is increasing in a particular orthogonal direction. And then this drds is kind of a geometrical shape. You know, how fast are two kind of lengths changing with respect to each other. So in order to evaluate this term, we're gonna zoom in on the geometry of the path at a couple of different times and see if we can't derive an expression that makes some sense. So we get a close-up of our path and our origin. So at time 0 or time t1, we've got a radius vector that's going to a point where we've traveled path length s here at P. And then at some other time, dt, delta t, the radius is pointing vector from the origin is pointing to this P prime, which is at s plus delta s along the path. So it's gone a little farther. It's gone delta s farther. So if I basically approximate my delta s with a straight line delta r OP, I can say, well, I can do some vector algebra and say that my ROP at s plus delta s is ROPS plus ROP at s plus the delta ROP. And then maybe look at manipulating terms. So first, I got a curvy length, delta s, and I got a straight length, delta radius OP. So the change in that radius from this radius vector to this radius vector. So this is pretty akin to that cylindrical coordinate r hat changing at two different times. So as your delta s gets smaller and smaller, the delta ROP becomes tangent to the path at P. So you can imagine these two things shrinking closer and closer together. First, the difference between the straight line and the curve really become insignificant, but we eventually end up with a point, a single point, where this delta ROP will literally be the tangent. It will be the slope of the curve at that point. It will be the tangent to the path. So the delta ROP will be by definition pointing in the tangent direction. This is sounding a lot like, the change in one unit vector being the orthogonal unit vector. Because we got a radius vector, which is sounding a lot like it's going to be a normal vector. Its direction of change is tangent, which is orthogonal to the normal. So we'll see how that shakes out. So now let's look at the magnitude of what's going on, because eventually we're kind of looking to see if we can define this crazy d ROP ds up here, because we need this for velocity. So as delta s gets smaller and smaller, this little delta path length between the radius vector at this point and the radius vector at the next point down, let's shrink that to 0. And we notice that delta ROP and delta S get closer to each other as delta S gets smaller. So the delta ROP over delta S becomes more like just delta S over delta S, which is 1. Okay. So the magnitude of this term approaches 1 as the deltas approach d's. And the direction of this term approaches the tangent to the path. Unit vector, tangent, orthogonal direction. So the length of the curved path and the straight vector approach one another. The path gets shorter, and our delta ROP becomes more like a tangent direction. So basically, we can again express this in terms of a definition of derivative and apply these two characteristics that we could see from our blown up geometry. So the d ROP ds, which we popped out with our chain rule, it's a unit vector because of this, magnitude 1, and it points in a direction tangent to the path. And that's the direction of increasing s. Path lengths getting bigger and bigger as we move down the path. We've traveled farther. So drOPDS we can express that as a unit vector in the tangent direction. So we say that's t hat for tangent unit vector direction. Okay, so ds dt is s dot. So the rate of change with time of the length of the path, the distance we've traveled down the path, and this drOPDS becomes s dot in the tangent direction. So v going down the path is tangent unit vector times the rate of change of the length of the path we've traveled. So s dot e tangent. So, and this is again, I've removed the O for simplicity. So this is the velocity of the particle traveling along the path. Okay, next we're going to want, of course, the acceleration, because we're going to want to somehow relate this to some force pushing it down the path or pulling it around. So let's just take another time derivative. So we're going to get s double dot times e tangent plus s dot times e tangent dot. So e dt e d e t hat dt. Say that 6 times fast. We can apply the chain rule again for this and define this in terms of the same way we did with radial and theta hat unit vectors in polar cylindrical, and get an expression for this term. The first time derivative of our tangent unit vector is again s times the derivative of our tangent unit vector with respect to s, not t. So basically ds dt times d t hat ds is going to be equal to d t hat dt. So it's a chain rule. So go back to the same kind of consideration that we just did to evaluate the t hat ds, and we find that we can express this in terms of our normal vector, the normal to the path. So we do that the same way, looking at our different normal or radius vectors from that origin again, and looking at the tangent to that path at one time versus the tangent at another time. And then we're going to squeeze that time together. We're going to squeeze that ds together, and we're going to look at the difference here between the tangent vectors. So first the tangent's pointing up in this direction, and as we go down the path, ds, now it's not pointing so far up to the top of the page, it's kind of pointing more towards the side of the page. Well, the difference between this direction and that direction is kind of downwards. So delta ET. And isn't that looking kind of a little bit more like it's pointing in a normal direction, kind of a radial direction at that point? Turns out that's exactly what it is. So the change in the tangent unit vector direction with change in position along the path is defined as the normal to the path at any given point. And that's changing with the path. With a circle, it's always pointing to the center. But this path is going wherever, so at every point along the path, the normal to the path is in a different direction, as is the tangent. So it's like a little traveling coordinate system that goes along the path. And the normal and tangent vectors are always pointing in a different direction, but they're always perpendicular to each other, and they define the other's direction of change. So we have that same kind of mutuality that we did in cylindrical coordinates. So as time change goes to 0 and our angle changes here, our change in our tangent unit vectors becomes parallel to the radius at that point, which is our normal vector. So we can go ahead and we can go through the same kind of argument that we did for cylindrical, and we can use a rectangular coordinate system to derive the same set of expressions using a cosine sine with an I hat, j hat reference to a particular path. We can get the same kind of expression. So we end up, when we look at our change in our tangent unit vector with change in path length, we've already established from this figure that it's unit vector in the normal direction. So let's look a little more at the angle that we're subtending and how we're going to express that vector normal at a given point, because that's always changing. Normal to which radius. So if we look on our figure down here, we got our same kind of path going along. We've got our tangent unit vector to the path at this point. We've got the unit vector normal to the path at this point. And of course, they're always changing as we move along the path. And we're going to define an IJ Cartesian system and a theta angle just to give us a reference to make some relationships. And so we can now say that our d t hat, so our change in our tangent unit vector with distance along the path, ds, we're going to use the chain rule again, is equal to the change in that tangent unit vector with respect to this angle theta times d theta ds. Why are we doing this? Because we have to get a little bit more information about what this normal vector is. Because our path is changing, we can't always define this in terms of, say, a circular radius. Hint, hint. We're going to get an ever-changing radius. Okay, so we can continue with this expression, and we can relate our tangent and our change in theta with respect to s using our cosine and sine relationships now with our I and j coordinates. Use a little bit of trig. So our tangent unit vector is cosine theta in the I hat plus sine theta in the j hat. And now we can take derivative with respect to theta, get negative sine theta plus cosine theta. That gives us our normal. Okay, so now we still have d theta ds. So we've confirmed first that yes, indeedy, dt, the change in the tangent unit vector with change in path length, it really is pointing in the normal direction. So we confirmed that with our little Cartesian expression the same way we did for polar. So our d tangent unit vector d theta is going to be pointing in the normal direction. And the opposite is true. Okay, so unit vector in the normal. But we've still got this term now. The change in angle with change in path length. This particular term is known as the curvature. And if we invert it, we get what's known as the radius of curvature. So if you've ever seen pictures of this, it's like drawing a little circle tangent to a curve at a given point and saying what radius would that circle have to define the tangent to a curve. So the straighter the curve line is, the larger the radius, of the circle that would be tangent to it, so it's got a larger radius of curvature. It's coming from this d theta ds term that came from this relationship, this leveraging of a Cartesian expression relating tangent and normal, the same way we did when we related radial and sort of theta direction unit vectors for polar cylindrical. So rather than having an r expression, we have a radius of curvature. So our change in our tangential unit vector with respect to distance traveled down the path is 1 over the radius of curvature in the normal direction. So this is like our centripetal sort of term equivalent to our polar cylindrical. So now we put it all together. We're going back into our acceleration expression. We had our s double dot, so our acceleration tangent to the path at any point in the tangent direction, plus the square of the tangential velocity, our s dot, times 1 over the radius of curvature, all of this directed in the normal direction. So our first term is tangential acceleration component. So this is changes in your speed in the path direction. So are you putting on the brakes? Are you stomping on the gas? It's all directed down the road, so to speak. This other term is the normal, and this is the term that makes you change direction. So if the road turns and you're going a certain speed and you've got a road with this radius of curvature, this is the acceleration that something gotta be providing or you're not going to make the turn. This is the normal acceleration that has to be provided in order to travel on that path. That's what defines the path. So very, very similar to certain components of our polar cylindrical, provided that the path is a circle. So basically, if we had a radius of curvature that was constant, we would end up with we would end up with a constant expression here, and we would have something that looks an awful lot like one of the expressions in our cylindrical acceleration, our momentum. Okay, so last little bit of this very long lecture, an example of our normal tangent. We got a car that accelerates from rest on a point on a circular track, and the car's speed increases by 6 feet per second. Speed increases, so this is looking like an S double dot to me. At what position in time does the car's total acceleration magnitude equal 20 feet per second squared? So now we're relating effectively the Pythagorean sum of both components of acceleration. That 20 feet per second squared is going to be picking up both our tangential and our normal. So we can write an expression for total acceleration using the terms that we just had. So we've got our S double dot is our 6 feet per second squared. We know that our radius of curvature is 200 feet. So now we're basically set up to solve for S dot at a given time. So we can do that pretty easily by integrating. So we just integrate our S double dot with respect to t. So that's going to be 6 feet per second squared t plus c1. Do we have an initial condition? From rest, accelerates from rest. So our S dot at t equals 0 is 0, so c1 is 0. So we have an S dot expression is 6 feet per second squared t. And so that should give us our total acceleration expression in terms of t. And so we can also get position, I think, what position in time does the car's magnitude. So we'll go ahead and integrate again for S. And remember, S is path length. So, you know, if we go around the circle once, our path length is 200 feet times 2 pi. So that's S for one lap around. So we'll just integrate our S dot with t, and we'll get our expression for total distance traveled, or S, our path length. And again, it started at 0, distance traveled, so c2 is 0. So here's our path position is 3 feet per second squared times t squared. So total acceleration magnitude is going to be the term from our tangential and our normal squared added square root. We're saying that has to be 20 feet per second squared, and we're going to end up having a time-dependent term in one of them. Here we have the 6t, so we can just write this and solve algebraically at what t does this sum equal the 20 feet per second squared. We get a 10.3 seconds, and then we can back substitute that into our expression for S and say, yea, verily, it will have had to have traveled 318 feet, which is about a quarter of a lap around. So that's just real simple direct substitution into our tangent normal expression for acceleration, given some fairly easy starting conditions. We happened to have a constant radius of curvature. We didn't have to. But to solve this, we would have, for a more complex path, we would have had to have some expression for how the radius of curvature changes with time, with some other position, so that we could relate them if we were going down some crazy curvy path. Or we would have had to have some point of interest where we knew what the radius of curvature was at that particular point. Otherwise, we couldn't have solved for it. But there's a lot of conditions where we do know what it is. So there's plenty of paths of very practical interest that use a circle. A lot of highways are designed where the horizontal curvature is circular. The vertical curvature is quite often parabolic. But this is a great example of something that is definitely used for things like road design. So knowing what these different accelerations are, especially the normal, is very, very important. that is it for our whirlwind treatment of examples of cylindrical coordinate applications, derivation of tangent normal being really similar to the r theta relationships for cylindrical, but with the twist of your radius term changing with your position on the path and therefore being expressed as the radius of curvature in terms of that d theta ds little expression. We could just remember it as a radius of curvature expression instead of an r in our normal component, and know that our tangent normal expression for acceleration velocity will be the same as a polar anytime we are constraining ourselves to follow a circular path. So if you get presented with a problem and you're not sure whether you're going to use, do I use polar, do I use tangent normal, just write an expression for your path and use either system. And if you start with cylindrical, just remember, if you stay on a cylindrical path, your r is not changing. And you'll find that you basically end up adopting the other one and they become the same if you make the right assumptions. So that is it for our treatment of particle kinematics. So the next topics that we'll pick up, we'll start into particle kinetics. So we'll start looking at all the forces that we need to cause all this cool motion or to stop it if we need to. And we'll follow up our treatment of particles as opposed to bodies by looking at work energy relationships and impulse momentum, which are kind of the second two ways of applying Newton's second law. So stay tuned for those exciting topics.